Hello dear friends, myself Sonigra, and today we are going to discuss about detail and assembly drawing of some standard components. Previously we solved numerous of examples based on detailed drawings, assembly drawings. Today also we will continue with some problems related to industries and solve the problems including all the rules and regulations which are used in the industries to show the details and assembly of a component. The objectives of today's discussion covers: the first is to draw detailed drawing from given assembly drawing, then to prepare bill of materials and solution of some typical problems. We will cover these three aspects in this present session. Now, what is assembly drawing? As we know, it is primarily used to show how a number of components are fitted together to make a complete product unit. The term subassembly is commonly applied to a product that combines with other subassemblies to make a complete product. For example, the assembly of IC engine, assembly of stuffing box, assembly of boilers accessories, mountings, etc. All this makes an assembly of individual components. These are the examples of assembly drawings. Assembly drawings may be divided into two categories depending on the proposed use. The first is general assembly, where the main purpose is to identify the individual components and show their working relationship. That is called as the general assembly. And second is working assembly or detailed assembly, or we know it as a detailed drawing. It's a combination and combined drawing, a combined detail and a general assembly drawing that fulfills the function of both the types. It may be assembly drawing, and it also shows the details drawing of the components. Simple assembly drawing. This is one assembly drawing or one assembly of four components. How to prepare simple assembly drawing of this component? So for that we have one animation. Let me see, which includes how to prepare assemblies of these components.
Parts as components, and demonstrate how you can use two different types of common mates to put the parts together. So what I've already done in advance is I've created these two parts. This is the first part and this is the second part. These are in their own part documents in SolidWorks. I'm now going to go to one of my parts. I'll just start with this one, and I'm going to create an assembly based on it. So that can be done using this Make Assembly from Part Assembly icon here, or File, Make Assembly from Part. Either one will work. So when I do that, starting from one of the two documents, I'll get this Insert Component screen. And if you click on Graphics Preview here, you can see the part follow your mouse as you move out into the editing area. Usually for the insertion of the first part into the assembly, instead of manually placing it somewhere, I just click OK here to accept the default placement. So if I click OK, now we are in a new assembly document, and I see that the mate part 1 here is placed in the assembly as a component. One thing to notice is that it's got this F by it, meaning that it's fixed in place, and it has by default been fixed in its default location in the assembly. So that means that if I were to click out here and try to drag it around, it can't be moved. The selected component is fixed. Okay. So now it's time to add another component to the assembly. So I'm going to go to my Insert Components icon here. I can also go to Insert Component, Existing Part Assembly. And since both of these documents are open, they show up in this selector here. I could also browse to a file that is not open. But I'm going to go and select my mate part 2 here. And this time I don't want to select the default position because it's right on top of the first piece. So I'm just going to put my mouse cursor out into the editing area here and just click somewhere that's not on top of the other piece. It doesn't matter where. So now I can see that these two pieces are in the assembly. I can move the second one around freely, and it'll even go through the first one. I can't move the first one around because this one is fixed in place. See over here that mate part 2 has a hyphen in parentheses by it, meaning that it is not fixed and can be moved around. Okay, so let's say I want to mate this this protrusion here to the groove over here, such that this is kind of standing up at a 90-degree angle like this. The best way to do this is going to be with a set of 3 mates between coincident faces, and the best way to show that is just to go ahead and do it. So I start my mate mode by clicking on the paperclip here, mate here, and I'm going to click on pairs of faces that I want to be touching each other. So I'll start by clicking, I'll click this face here, and I want that to be touching this face. So the component moves into place, and I can click OK here, or this check button here. I'm going to temporarily leave mate mode just so that I can show what's happened here. So now when I drag this piece around, it's moving in such a way that this plane here and this plane here are coincident. So if I get a view like this, you'll notice that I cannot move the piece up and down. Okay. So I still have a lot of range of movement here, so I need to add 2 more mates to get this fully in place. So let's go back to our mate tool, and I'm now going to mate this face here with this inside face here. Okay. So now I can only move the piece like this. I can't move it this way, and I can't move it up and down. So the last pair of mates that I need to put in will be between here and here. Okay. Now notice that the hyphen in parentheses has gone away, because mate part 2 is now fully defined in this assembly. It cannot be moved because it's got just enough mates to fully define its position in the assembly. So there's no more moving this around. Okay. All right, let's go ahead and add another piece. I'm going to actually, I think I want to add another copy of that mate part 2. So I'll go ahead and insert that here. Now notice that both of these are instances of this part called mate part 2. So if I were to go back and change that original part, they would both be updated in this assembly. They're not separate. Well, they're separate instances of the same object, but they're not separate objects. So this time, let's say I want to put this peg here and this hole here. I can do that using a concentric mate. So again, I'm going to open up the mate panel, and I'm going to click the outside cylindrical surface of the peg and the inside cylindrical surface of the hole. So let's see what that did. So now you can see that these inside and outside faces are lined up in a way that the pieces have to be right on top of each other in this way, and the freely moving piece that's not fixed in place can be rotated like this. I've also got this motion up and down because it's not taking into account the fact that the peg stops here. It's extending that cylindrical surface infinitely up and down. Same with the inside surface here. So I actually need one more mate to get that in place on the peg, and that'll be a mate between this face and this face. So we can do that. Here and here. So now the part is in place. It can't be moved off the peg because I've stuck these two faces together, but it still can be freely rotated. One last thing I want to show is that by default I can move objects through each other, which may not be what you want if you're trying to play around with something, how something behaves in reality. So one last thing that we can look at. Usually in an assembly, dragging things, just clicking and dragging will move things, but there's also an explicit move component tool here. So if I go in here and I click on collision detection and say stop at collision, now if I move things, it'll stop when it runs into something else and make a little beep on your computer. So now I can see exactly how this piece could move without going through other material. So that's a good way of investigating how your pieces interact with each other. And notice that it's highlighting the parts of the faces of the part that are crashing into each other. Let's just add one more mate here. or one more part. I'll insert the original part again, and we'll just mate this. Whoops, that edge isn't what I want, so I accidentally selected this edge, so I'm going to go back here and press the delete key to get rid of that in my selection. So I want this face and this face. Okay, then I want this face and this face. And finally I want, say, this face and this face. Notice that I just mated these two faces together. They don't have to be touching. It's just that they're sharing the same plane. That's what the coincident faces means. One last thing that I should show, and we'll add one more part for this. I'm not going to fully mate this. I just want to show one thing. For every pair of coincident faces that are mated, there's actually two directions they could be mated in, and sometimes you need to flip them explicitly. So let's say I was going to mate this here with this face here. Okay. Now maybe this is what I intended, but I may have also intended for this to be the mate. So you can get there with this flip mate alignment button that's also available down here in the mate property manager. So that's something to keep in mind. If by default SolidWorks decides on the wrong orientation or the orientation that you hadn't intended, you may need to flip around the mate alignment this way. Let's get rid of this. I'm going to delete this component. Notice that these two, even though they're locked to each other and to the base component here, in a way that I could do this, they're not fully defined because they can still be moved somewhat, and that's fine in this case because I want to be able to do this rotating motion. So those are the coincident faces and concentric mate type.
So that was regarding how to prepare assembly with the help of solid edge. Now in general assembly, some features are there. The features of general assembly drawings are views that show how the parts fit together and now the unit may function are selected. These views are often sectional views which eliminate the use of hidden detail lines where possible. Individual components are identified by the use of numbers contained in a circle. Balloons are used. They are connected by leaders to the related parts, and sequence numbers are given 1, 2, 3 onwards, and those sequence numbers are represented in bill of material as well. And individually names are not written in every parts. Dimensions that relate to the function of the unit as a whole are indicated. This is not compulsory. In some cases, the dimensions as a whole may be indicated to show the function of unit. A parts list related to the numbers on the drawing are identifies the component, and a revisions table is provided to record modifications to individual components that may occur from time to time. It may be needed to revise any dimension, any manufacturing process, or any parameter, or as on some date. So those dates and numbers of revisions are mentioned in the revision table, and it is frequently updated as and when needed, time to time. This is one typical example of general assembly drawing, which includes the balloons or part list. Say this is the part list. These are the numbers of parts. Say part number 1, it is jack body, this one. Number 1 is a spindle as shown over here. This one is the spindle. It's a machine screw jack. In this machine screw jack, number 1 is this one, it's a spindle. Number 2, this one is a spindle cap. Number 3, this one is a standard washer. And number 4, this one, this is the jack body of the screw jack. And here this assembly is drawn over here, showing 3 views: front view, top view, and side view. And as the top view is drawn over here, the symbol is representing over here. The symbol shows it's a third angle projection method. and a revision table is drawn over here. Say revisions, symmetry A, in component A revision is made, and whatever revision is there, its a description is shown over here, reference number, date of revision, and approved by, that is represented in the revision table over here. And some para dimensions, that is minimum operating height 78 mm and maximum operating height 125 mm, is shown in this assembly drawing. Name of component, name of company, and some other details like drawing number, drawn by, designed by, checked by, and scale are also represented in this assembly drawing. So this is the assembly drawing taken from a Shambles Private Limited to show the details of to show the assembly of screw jack. Now assembly of connecting rod. How connecting rod is assembled together, we have one video clip that we'll see. Here these are the components of connecting rod. This is the connecting rod, and the assembly is made here with the help of SolidWorks. So let me prepare an assembly with the SolidWorks. Call all the components one by one. First it's a fork end, so here fork end is called over here. This is the fork end of the connecting rod. Now we can call another component, that is tie rod. So this is the tie rod. It is assembled like this. Here threads are provided, and through this external thread it is inserted in the internal thread shown over here in the fork end. This one here, threads are there. So when this eye end is rotated, here mating is made. These threads are made with this, the external thread of the fork end. So it could be inserted like this, and here threads are provided so that we can easily disassemble this connecting rod as and when needed. It's a highly sophisticated connecting rod in which all these facilities are available. In general, now we call one more component, that is let we call this one bush, and this is inserted over here at the another end, or it forms the small end of the connecting